Okay, in part 2 of this guide sheet video, we're going to be going over acceleration as a rate quantity, how to calculate the value, the numerical part of acceleration. So acceleration is a rate. It is the rate at which velocity changes, so it's change of velocity divided by time. Velocity has both speed and direction, so it might be a change of speed or a change of direction or both. Objects with high acceleration, this is where it gets tricky, are not necessarily going fast. Okay, they are rapidly changing their speed and or their direction. So they might be getting fast, really fast quickly, but that doesn't mean they started out going fast. They might be slowing down very much, but it doesn't mean necessarily that they were going very fast, or that in the end they're even going very slow. It's about the change of speed. It's not really the thing you easily see. You see the velocity. You have to have a feel for the acceleration. Now, it's a rate of change of a vector velocity, so therefore it's also a vector quantity. It will have both a magnitude and a direction. In equation terms, we say it's the rate of change of velocity, so delta for change, v with an arrow because it's a velocity, it's a vector. It's the rate, so we're going to divide by the time. Now, we're talking about some delta t, some time interval, time A, time B, time now, time later. To separate the two different velocities, we're going to use f for final and I for initial. Delta essentially means mathematically difference. So difference is to subtract. So we're going to take the final velocity minus the initial velocity. And it's always in that order if we're trying to keep an appropriate track of direction. Okay, so now what does it mean? We need units to measure it in. The units are going to be delta V, which is meters per second, some change in speed, the base being meters per second, divided by however much time we measure the change in. So that's divided by seconds. So we say for acceleration it's meters per second per second. Now that is often shortcut written as meters per second squared. Now it doesn't have to be meters in seconds, it might be miles per hour every second, miles per hour for every minute. Any unit of speed divided by some unit of time will work. The base, the best, is meters per second per second. Now the shortcut method of meters per second squared, it's quicker to write, but it's not as descriptive. So I always prefer to write it out as often as possible like meters per second per second. Okay, so we have an acceleration of 10 meters per second for every second that we're traveling. Again, that's delta V is going to be 10 meters per second. So we're changing our speed or our velocity. The velocity is what we're changing. We're changing the numerical part of that by 10. And then that's per second. So the correct answer here is it's the velocity that we're changing. Acceleration is the rate of change of velocity. And we're doing that 10 meters per second for every second that we travel. So the correct answer there is B. Or it's not telling us how fast we're going. It's not telling us about the distance we're traveling. It's telling us about the change in the speed. Now, in this case, we have multiple data points. They're constant in terms of their change, so we can pick any two to be the final and the initial. I do need a delta V and a delta T. So let's take this one and this one. This is where we're ending, so this is going to be final. This is where we're starting, so that's going to be initial. So I'm going to take 40 miles per hour minus 0 miles per hour. Divide that by delta T. We started at 4 seconds. We ended at 4 seconds and we started at 0. Okay, the zeros go away. We've got 40 divided by 4. That's 10. Now the units this time are miles per hour of speed change, velocity change, divided by seconds. That's an S here, not a 5. So 4 seconds. So mixed units there. It's miles per hour per second. Could not use a miles per hour squared in that case. It doesn't work. Okay, Mr. Henderson's imaginary Porsche accelerates from 0 to 60 miles per hour in 4 seconds. So again, 0 is going to be the initial velocity. That's I. 60 is going to be the final. And then this is the delta t, the time that took. So our acceleration is 60 miles per hour minus 0 divided by 4 seconds. 60 divided by 4 is 15. It's 60 minus 0, so the answer does come out to be positive. It is miles per hour per second. Okay, it's not meters per second. It's miles per hour every second that he travels. So if you just kind of think that one through, it's at first he was at 0. 1 second later he went up to 15. Another second later he was at 30. Then he was up to 45, and finally after 4 seconds he was up to 60. If he can maintain that acceleration, then 1 second later he'll be up to 75. Okay, number 7, car speeds up from rest. Rest is an important word. That means that your initial velocity is 0. 2 is 16 meters per second positive in 4 seconds. So again, we're looking for acceleration. This plus 16 meters per second is going to be our final velocity. This is going to be our delta t. So it's 16 meters per second minus 0 divided by 4 seconds. 16 divided by 4 is 4. And that's going to be positive. And it's meters per second for every second that we travel. Again, if we can maintain this acceleration, then after 1 more second, we would be up to 20 meters per second. So it's not telling us directly how fast we're going, it's telling us how fast we're getting faster or slower in this case. Now this turned out to be a positive value, and we were getting faster. That is not always necessarily the case. As we'll see in the next clip, it could be that we have a positive acceleration and we're actually getting slower. It's a combination of which way you go and the acceleration rate that determines if you slow down or speed up. Okay, our next one it tells us we're going to slow down from 32 to 8. So this is actually VI, that's how fast we were going. This is VF, this is our delta t. So our acceleration is positive 8 meters per second minus 32 meters per second. Now notice these are both in meters per second, so we can subtract them. If their units didn't match, we wouldn't be able to subtract them. So make sure your units match. Divided by 4 seconds. Now 8 minus 32 is negative 24 meters per second. We're going to divide that by 4 seconds. That gives us negative for the answer 6 meters per second per second. So that is our answer. Now this TAMA came out negative and we did slow down, but again, not always true that a negative acceleration means slow down. That's a common misconception. Oh, we're always going to use positive acceleration for getting faster and negative acceleration for getting slower. Not true. You have to look at the comparison of the velocity and the acceleration. In this case, we had positive velocity and negative acceleration. When these two are opposites, we slow down. Up here we had positive velocity and positive acceleration. When these two match their direction, then we get faster. So it's not just that negative means slow down, it's a combination of what's the current velocity, what's the direction of the acceleration. Okay, so that finishes the base calculations of acceleration. We'll look at this idea of the vector nature to wrap up next time.